further ado, Claudia, the floor is yours.
Thanks for the introduction, and let's get started. We have a lot of to cover today. So as announced, I will talk about chances and the meaning of opportunities and challenges of machine learning in cybersecurity. So what I'm going to cover is that I want to give you a basic understanding of what machine learning is. We will learn about different types of machine learning, how they work, and see areas where machine learning is already applied in cybersecurity. But we also want to discuss challenges and problems that are related to machine learning in cybersecurity. So the goal is that by the end of this talk, you should have a solid overview of how cybersecurity can benefit from machine learning, but also which challenges and threats and problems are related to it. So it's more meant like an introductory talk to the topic and not a real technical deep dive, but I hope you get a few things, inspirations that will then help you to maybe dig deeper into this topic. So just 2 sentences about me. David already introduced me. So I'm a senior security consultant at Enviso, where I'm mainly focusing on penetration testing, so web and mobile application security. But the interest in machine learning, I actually got that during my university studies, where I dig a bit deeper into reinforcement, especially. We will come to that in a second. And I'm now really curious to see and explore how I can combine kind of these 2 really interesting topics, machine learning and cybersecurity. So first, is machine learning for cybersecurity at all a thing, or is it just kind of a hot topic by making it some propaganda or marketing stuff? So if we think back traditionally, security problems are aided by mathematical models, such as think about cryptography. But those models have limits when it comes to a very large number of variables we have to consider, and if we have to process a huge amount of data. And these are areas that are actually the strength of machine learning. So this is why it is indeed a thing we can use or we should cover when talking about cybersecurity, also because a lot of companies are kind of adopting it. But a word of caution, not everywhere where machine learning is written on the outside, it's actually on the inside. So because there are overlaps between machine learning and just simple statistics, some vendors might claim they are using machine learning when actually they are just applying simple statistics in the back. So it is indeed sometimes more kind of like of marketing thing, a propaganda thing to make look things nice and shiny. So with this in mind, first, let's get our terminology straight. So there are terms like artificial intelligence, machine learning, deep learning flowing around, and often used interchangeably, although they aren't exactly the same thing. So artificial intelligence is actually the broad field and study of simulating human intelligence, while machine learning is a subset of it, an approach to enable computers to make decisions on their own and do stuff and things they were not explicitly programmed to do. The phrase was coined back in 1952 already by Arthur Samuel, a pioneer in the field of computer gaming and artificial intelligence. So it has been longer around than one might think, but it has formally limitations due to the computational power it requires. And this is also the reason why it's kind of gaining momentum during the last decades. Now, deep learning, again, is just a subset of machine learning. So it's certain techniques applied within machine learning that is about simulating the behavior of the human brain. And we will come back to this a bit more in detail later during this talk. Now, also, machine learning is not just one thing, but there are actually different types of machine learnings, and all are suited for different types of tasks that we want to achieve. We usually divide between 3 different types of machine learning: supervised learning, which might be the most commonly known and can be compared to learning with a teacher. So you kind of have someone or something that tells you exactly what is what and what to make of this things you see. And it's mainly used for prediction. So we want to map a certain input we have to a certain output. And the most commonly known subcategory here is classification, where the predicted output is categorical. So think of it in the example of image recognition. So we give it a picture and we want to know if we can see here, for example, a cat or a dog. If we want to predict some real valued output, then we are talking about regression. So this can be applied, for example, for weather forecasts or market forecasting. Also in unsupervised learning, we have different subtypes. Unsupervised learning can be compared a bit to doing self-studies. So you don't have anyone telling you what to make of the things you read and study, but you have to kind of organize and structurize it on your own. And so you usually use it, for example, for like of pattern detection and structurizing data. So clustering, for example, is about grouping input into segments based on certain similarities. So the machine learning algorithm is to kind of find those similarities and group the data according to it. We have association rule learning, which is about finding correlations. You might have always seen this, for example, if you get proposed products in Amazon, or if you have kind of like Spotify and your weekly discovery playlist or something like that. And it's based on the probability that we see two events occurring together. So kind of if you like song A, there is a 80% chance that you also like song B, because this has been observed together very often. And as a third type of unsupervised learning, we have dimensionality reduction, which is often more like a pre-processing or intermediate step. It's for filtering and reducing data, so reducing the dimensionality. For example, if we want to create visualizations or if we want to process the data further and want to kind of reduce it for that purpose. And last but not least, we have reinforcement learning, which can be compared to learning with a critic. So someone who doesn't tell you up front what is what and what is right and what is wrong, but will give you feedback based on what you did before. And what it's used for is like learning procedures of actions based on the feedback you get. And we'll have a closer look on all those three types and how they are applied or can be applied for in the field of cybersecurity during this talk. But first, let's see the basic machine learning process you usually have. And it all starts with gathering data, because data is kind of the fuel for machine learning. So we need it for our training process. And like with fuel for a car, the quality and quantity we have has a direct input on the results we get. So if you have bad fuel in your car, it might destroy it or it might get you very far. The same is for data in a machine learning algorithm. Now, next, we want to prepare the data. So kind of, for example, randomize the data samples, but also very important, check for biases. So, for example, is there a certain type of data very dominant in your data set? And if yes, your result will also be biased toward this type of data and will be struggling with other types of data. So the very kind of famous or infamous example for that is the early phases of face recognition, which were mainly trained on images of white people. And then, of course, the algorithm struggled with the faces of people of color. Now, something else we want to do is split our data set into a training and evaluation data set. So usual ratio here is something like 80-30 or 80-20 or 70-30. So you have a larger training than evaluation data set. But we need the evaluation data set a bit later, as we will see in a minute. Next, we choose a model. So a model is kind of the raw material we have. It's a generic program that is then made specific by data. So think of it like clay, which will then get molded through your hands by repeatedly molding it or turning the wheel or something like that. So we, of course, have to choose here which learning algorithm we want to use. And there are, of course, multiple algorithms out there. So there's not just one for classification, one for clustering, but there are a lot of different types. And what you have to choose is, of course, the right algorithm that's suited for your purpose. So is it at all a classification task? Is it more a clustering task? And which algorithm for this task is the best or could be the best for your case? Next, we start training. So this is the learning process that forms the model until we finally have the result we want. And it's an iterative process. So we do a lot of training loops during which we make repeatedly small changes to our model until we finally get the result we want. And to check whether we've reached that state, we, of course, need to evaluate our model. So we run our model on the evaluation data set. You remember step 2, where we took this out. So we give it data it hasn't seen before to check its performance on unknown inputs and see whether it can work with that. So you have problems, we will come back to this later, where you might have not trained enough and it doesn't perform well on the data set, or you might have trained too much and then it also doesn't perform well on the evaluation data set. So based on the outcome, you will start tuning your algorithm, so certain parameters you use, and try to optimize the performance, for example, get a greater prediction accuracy. And last but not least, you can finally apply the model. The step is also called inference. So putting the machine learning model into production, use the trained model actually to solve the task you would like to solve it. So let's look at this process a bit more in detail in the different types of machine learning we've seen. So at first, let's look at the supervised learning. And here, let's choose an actual example from the area of cybersecurity, a very typical one like spam detection. So this is a classification task. We want to predict an output that's categorical. So is it spam? Is it not spam? And what we need first in the training process is label data. So, or we need two things. We need the labels. This is what we want to predict, like spam, not spam. And we need labeled data. So in this example, a lot of emails for which we already know this is a spam email and this is not a spam email. Now we will describe each data point through a feature or attribute vector. So this is the criteria based on which we will then train our model and later make our predictions. So this is actually data or are features that are probably relevant for our classification here. So in the example of emails, this could be, for example, the sender address or contained links or attachments. But something like, for example, the date and time of receipt might not be a feature that's really important and relevant for predicting if something is spam or not. Next, we start the training process. As I said, it's an iterative process where the learner develops a model, or shapes the model based on the training data. And once we have finished the training process, or also in between, we then run some evaluation to see whether we first have to maybe change and tune some things here. So what we could change, for example, is of course some parameters in the algorithm itself. So in the training part, but also maybe make changes to the feature metrics if we see maybe a feature might add a feature that might be helpful or remove a feature that we don't think helpful. And this all can change the outcome. So after completing the training process, then we can use it for prediction, which will mean we get an email. Also have to extract the feature or attribute vector as we did for the training data. And now we'll put it or we'll give it to the model that we've trained. And as a result, we get back a certain probability that the mail we gave it is a spam or a non-spam email. The same principle can be applied, for example, or is already applied for malware detection, where you then, of course, have extract features from a binary to see whether you have or whether it's a good or bad executable, for example, you're dealing with. Now, for those who thought, oh, this is really interesting, I want to do this myself and get my hands dirty and give it a try. What you need, of course, is some data, and there are data sets out there you can use. For example, for training your own spam detection algorithms, that the spam-based data set from the University of California, Irving, and that has about 5,500 emails, of which about 13% are spam emails. So you have the labeled data there you can use. And also for malware, there are data sets like Microsoft's malware dataset or Endgamer's Ember malware properties dataset that you could use if you just want to try it out and try training a model on your own in these tasks. So what does the process now look like, or what are the actual differences in the process now for unsupervised learning? As we remember, this was more for organizing and structurizing data. So the first difference is that we have a completely different input here, which is we get unlabeled data. So as I said, we don't have something that already tells us what is what. We just get data as it is. And again, we must describe it through a feature vector and start the training process and shape the model. And as an outcome, usually then there is some human intervention needed and required to interpret the output we get at the end from the model. So the algorithm, or we will get back some type of clustering, for example, and we will then actually have to detect what is the points or the reason that the data was clustered that way. So taking the example here, what we could end up with is, for example, like on the left, we got 2 clusters based on the shape, as we can see, and on the right, we got 3 clusters based on the color. So this is why we then here need still some brain to see what we get as a result. Now, where could this be used? For example, 2 areas of applications are user behavior analytics and forensic analysis. So in user behavior analytics, what we want to do is, of course, find anomalies in user behavior and detect insider and outsider attacks. So parameters you usually look for example, IP addresses and their geolocations, timestamps, user agents, or certain actions that are done. And if you look at it as a very simplified example here, you can say that the behavior of admins has some typical traits, putting them into one group. So kind of like the blue cluster you can see here. And the typical behavior of your users is in a different group. It's like the yellow cluster here. And if now an admin, for example, logs in from an unusual IP address, one that's usually associated with a normal user, for example, he moves out of his admin cluster. So what we can do very well with unsupervised learning here is detect outliers and things that do not fit into or do not fit into their usual cluster or into a cluster at all. Same goes for forensic analysis. So, for example, if we try finding anomalies in log files, which are usually huge, this is really of help here to process this amount of data and to find things that really stick out and can be indicators of attacks or compromise. So outliers could be, for example, data that doesn't match any other data, or something that's unusual in terms of frequency, in terms of correlation on sequence. And there are tools out there that already use unsupervised learning, usually with a deep learning approach, which I will explain in a second. For example, Splunk or Darktrace are tools for user behavior analysis using unsupervised or using machine learning, unsupervised learning to do this task, or forensic analysis. You have the Elastic Stack, which is free and open source and helps you actually create your own machine learning jobs to analyze and monitor metrics from logs. So we also see there kind of a machine learning becoming easier available to end users, so you don't have to really understand the deep technical stuff anymore and the mathematics behind it, but it's kind of getting more user friendly and more easy to use. Now, last but not least, on the types of machine learning, reinforcement learning, which differs a bit from the two things we've seen now, because here the agent, or we call it the agent, so let's call it the learner, the one who learns, is creating their own learning experience through interaction with an environment. So we don't have data beforehand. And it's like learning through trial and error. So the best example to think about this is, for example, a cleaning robot. So if you think about a cleaning robot running around in your house, what it has certain sensors attached to it, which will give it a certain state. So for example, it will see, my front proximity sensors detect something very close to me. Could be translated to like I'm standing in front of a wall, or at least in front of something. So, and based on the observation, it now tries to choose an action, and it has a certain policy, which is kind of its current knowledge, that helps the agent, or in this case, the robot, to select and execute an action. So possible options would be here, for example, move front or turn sideways. And as a result of taking action, we have another observation. So, for example, after moving front, the agent will detect, my bumpers detected that I hit something. Or when it turns sideways, it will say my front proximity sensor, see there's nothing in front of me anymore. So based on the observation we first had, the action we took, and the new state and observation we are in, the agent will receive a certain reward, so kind of which indicates whether the action was good or bad. So kind of if we bump against the wall, that's bad. We give it a negative reward, meaning basically a negative number usually. And if we detect we have now a freeway, we give it a positive reward, so kind of a positive number to say this was a good result. And over time, this then shapes the policy. So the reinforcement learning algorithm then modifies the behavior over time, because the agent's goal is to maximize its rewards and get as many positive rewards as possible. And this will filter out the bad behavior over time. But of course, it's time consuming. So your agent will probably bump the wall around 1,000 times before it starts learning that it's actually bad, what it's trying to do there. Now, for the application of it in the area of cybersecurity, there are some challenges, as I said already, that it is time consuming, but also the thing is that real world problems are usually have a large state and action space. So a lot of possible states, a lot of possible actions that could be taken. And as a consequence, reinforcement learning is now usually combined with deep learning approaches. We come back to this in a bit. And this is still a quite new thing. And the first great success with this was in about 2015 with, maybe you've heard of it, AlphaGo by Google. So kind of a machine that taught itself playing the board game Go, and then became so good that it defeated not just the best human players, but also the best machine players around at that time. So so far, the greatest success of this has been in other domains like video and board games, or even robotics and autonomous driving. But there are some scenarios where it's considered and experimented with in the field of cybersecurity. So one thing is, for example, cyber physical systems. So meaning IoT, industrial internet, smart grids, smart cities. So basically everything that's smart. And you take the sensor input of the sensor input of the device defines its states, and by training it, certain changes in its state and in the sensor input might help it to detect if it's, for example, if it's under attack, and to select the appropriate action. So you kind of get a device that can defend itself because it knows how to react and which actions to take if it detects some malicious things going on with its sensors. Another area where it's applied is for intrusion detection systems, but more as an addition to other learning approaches, so combined with supervised or unsupervised learning. And the aim is to enable systems to choose more appropriate log files, for example, when looking for traces of an attack, by giving kind of a additional reinforcement loop, which will give a reward or a penalty when a system selects a log file that does or does not contain anomalies or signs of an attack, so that over time the system will get back better selecting those log files. And a really interesting area of application is the one of game theory. So with game theory, we can model the conflict and cooperation between intelligent decision makers. So basically describing, for example, an attacker and a defender fighting over an asset. And this is exactly what was experimented with. So you have two agents, the attacker, the defender, both act against each other and try to learn the optimal attack and defense strategy. But the problem with this is that it, of course, simplifies the real world cybersecurity problems into a very limited game of just two players and with 1-2 assets, which is usually not the case in the real world. Now, the most common algorithm use, as I said, is when you combine reinforcement learning with deep learning. This is why I want to give the deep learning also a closer look. So deep learning usually refers to the use of neural networks. And the neural networks is based on the working principle of neurons in our brain. If we look at a model of an artificial neuron, we receive a certain input. So in real life, certain certain input from our senses, and those go through synapses into our neuron, and those synapses have a certain strength that amplify or weaken the input. So these are called weights in the artificial neuron, and this determines of which input is more or less significant for our case. Now the neuron will sum up all the input we get and then compare it to a threshold value. And if this threshold value exceeded, the neuron will fire, and meaning it will produce a kind of a positive output, which is also called the activation function. Now, in deep learning, we have multiple layers. So a simple neural network just has the one neural layer in between. In deep learning, we have multiple. So the input of or the output of one layer is the input of the next layer. And each layer will bring more complexity to the table. So thinking about image recognition, it's so the first layer might be able to identify edges. The second layer might identify combination of edges. The third might identify certain features like eyes or mouth. And the last identifies combinations of features like a certain face. Now, so how does the learning then work in those networks? So the training means that we will again have an iterative process where we tune those weights, so the strength of the synapses and the biases, so the threshold values within the neurons, in each neuron, in each layer, until we finally get the get close to what we want. So at the end, there's always a so-called cost function, which will determine the degree to which the output we get now differs from the expected output. And the result is then pushed back across all the neurons for tuning those values. I see I'm getting a bit dark here. Let me enlighten myself a bit. Okay. Now, having learned about the basic principles, let's sum up a bit on the opportunities, how we can actually use this for our purposes. So we've seen already some examples, but the main areas where it's now applied and indeed it's promising is automation, for example, so that it takes over repetitive tasks such as triaging or log analysis, or so that human analysts can then actually concentrate on the really difficult stuff. Also, most promising is again to actually combine it with humans, so enhance human analysis, for example, to reduce human error, but also to increase efficiency. So there was a very promising experiment at the MIT's Computer Science and Artificial Intelligence Lab called AI Square for log analysis. And what they did is that they had first supervised learning algorithms that finds extreme and rare events and logs. And those events get then reviewed by human analysts, which will label them as this is normal or this is indeed an attack indicator. And now we have labeled data and can feed this back in a supervised learning loop. And based on this input, then, and also the one it got from the unsupervised learning part, can do a prediction if an attack is imminent or not. And during this experiment, the attack detection rate actually rose to 85% and heavily decreased the false positives. Also, it can help us to improve threat response time. So by pulling the data actually required or really relevant data from log files, so we can prepare them for analysis, so that cybersecurity teams get more simplified reports, making the most important things or highlighting the most important things, and then can make decisions faster. And it's kind of like, of course, the dream that maybe also at a certain point of time, machine learning might be able to detect 0 days. So there have been, of course, some studies and experiments on this, but I'd say we are not entirely there. So usually if you have something completely new, your model has never seen, it of course will have problem dealing with it. So we're not quite there yet. So there are, of course, some problems and challenges, as I already mentioned. I already said you have general problems during the training, like overfitting. It's like you train on your data set, like learning for a test and getting sample questions and learning exactly those sample questions and their answers. And then you get in the actual test different questions and you perform bad. That's the problem of overfitting. Underfitting means we have not trained it enough, so we have not studied enough, and then we also will not perform well. Also, a problem is always dimensionality. So the more dimensions and factors and features we have to learn, the more data is required. And again, there's this inductive bias. So there are certain assumptions we make, for example, when extracting the feature vector. And this has, of course, an impact on the results we get. And especially in cybersecurity, a huge problem is also the shortage of data, or especially the shortage of labeled data. And then the imbalance of data set we have. So usually your ratio should be something like 1 to 10. So in 10, 10 normal emails have one spam email, for example. But in cybersecurity, this is usually a lot higher. So you have a lot, for example, a lot of benign traffic and just a very few malicious samples. Also think about the consequences. So if your model does produce false positive, you lose work time and confidence in the system. But think of the false negatives if your model isn't working good enough. So the worst cases, of course, you can have a full system compromise. And another great problem is that often we want results to being interpretable. So we want to know why a certain output is made. So why did the algorithm choose maybe, for example, a certain log file or a certain, why did it suggest us a certain category in classification? And it's kind of difficult to see under the hood on which basis this is made. So it kind of makes it difficult to explain. And of course, the world changes usually quicker than models, or there's always time, as I said, required from changes until a model can adapt to those changes. So you have new protocols coming up, new types of activities and malware. And this is, of course, also a challenge. So my last 5 minutes, let's look on the other side of the coin. So we've seen a lot of cases where we could use machine learning, but also have a look at how machine learning can be abused. And the first CVE for a machine learning component was published in 2019, which was for an email protection system. So you see the attackers never sleep. And by the end of 2020, Mitre, in cooperation with Microsoft and other companies, published this adversarial machine learning threat matrix as a framework for detecting and responding and remediating threats. So in highlighted in white are threats that are really on techniques specific to machine learning systems. And as you can see, there are quite a lot. And in gray, there are techniques that are applicable to both machine learning and non-machine learning systems. And due to the time, I just picked 2 very small examples to demonstrate this. 2 types of attacks here, poisoning and evasion. So poisoning is something that usually happens during training, meaning the attacker is somehow able, for example, to modify labels if you want to do some classification, or to inject adversarial samples into the training data set. And the best example for this is actually from 2016, Microsoft's chatbot Tai, who remembers this. So this was a chatbot program to learn from interactions with users. So the user text it got was actually the input, and it had to be taken down 24 hours later as it has become sexist and racist. So means, of course, if you give it poisoned input, you will get poisoned output. And another very famous example is evasion. It's kind of like the most common type of attack you have. So you try to design input that is then wrongly classified by the machine learning model. And I've chosen here an example from DEF CON 2019, the stealth shirt. So you have an object detection camera. So whenever you've seen the green square, it detected an object. And as you can see, whenever he doesn't cover the front of his shirt, he is not detected. So this is how the stealth shirt works, to kind of confuse the algorithm so it doesn't detect the model. And this has also been shown in research, for example, by putting stickers on stop signs, which then get misclassified try to no longer stop signs, but like speed limit 30 or 50 signs, which is, of course, if you think of autonomous vehicles, really bad if this was a successful attack. And last but not least, of course, we cannot just attack machine learning, but we can also use machine learning for our attacks. So with everything can kind of be used as a weapon. And there have been some examples showing this successfully, like breaking the Google CAPTCHA with machine learning, or generating passwords, so creating more concise lists based on data on the user, which make password cracking then more successful. That you create malware that can then evade anti-malware engines, or also for advanced phishing attacks. So, for example, the tweets phishing posts targeting a specific user and seeding those posts dynamically based on topics extracted from the timeline and posts of the target and the user he interacts with and retweets and follows, which makes it then really hard to detect that this is indeed phishing. Okay, this concludes my presentation. I hope you gained a good overview of the topic, and I'm happy to answer questions now.
Great. Thank you very much, Claudia. Let's wait a little bit to see if people have any questions. Again, you can write the question here in Zoom or even in Slack. We will answer those. In the meanwhile, I want to ask something, Claudia. First and foremost, great presentation. Thank you very much. I feel like it was very informative, and especially talking about a quite complex topic. It could be, it's actually easy. It has a lot of stuff going on, a lot of moving parts, but I felt like it was really easy, brought down and sent to us, so that was great. I have a question now then. Have you surveyed, or do you have an understanding of how machine learning has been applied in nowadays cybersecurity solutions, on what the one that they claim that they have machine learning on their solutions? And if you do, what you think about that? Is there something that you want to comment on those?
Just let me repeat your question to make sure, I understood it right. So, where has it actually been applied? How well, basically, or?
In general, I was asking if you had a look at other softwares or services in the internet that they claim that they promote machine learning as their product. Okay. If you have a look at, what do you think about implementation?
Of course, this is usually the problem, that you can't really look under the hood of the product. So, because this is kind of what their business is built on. But for sure, you can see that, so it's mostly now in let's say more products for the blue team, like I said, like Splunk or Darktrace. So they couldn't do what they do if it wasn't real machine learning, or more concrete, really deep learning that they apply. So you can be pretty sure they're actually using it. The question is, you get very little information on what exactly they're using. So they usually, of course, say, okay, we have some deep learning applied here, but they won't give you details on the models, or often also not. So it's often also the question, what training data do they use, for example, to actually get their models trained? This is also something you should maybe ask the vendor when you consider using their services, but don't expect them to really give you a very informative answer on that, because that's a kind of part of their secret.
Yeah, I can imagine that they can, play in this regard, what they have. And also understand that some of them, they just, it's not that easy to figure out if someone is using that but it's good to have some pointers and especially understand, right, if the outcome is expected to be from machine learning or just a bunch of, I don't know, cron scripts, and then they just analyze the data, and then so that's why I was asking if you had any of the experience.
Yeah, so you can be actually pretty sure if you have those large, really, really large amounts of data. The best way to handle this for those use cases I showed is machine learning. You can't actually, or would take a lot of more processing power to do it otherwise. And so it's kind of also the economic option to go for, to use machine learning in those cases.
Makes sense. So we have a question from Pablo. Do you know any example of use of machine learning to estimate risk? For
risk estimation,
I think he's referring more about business risk or this kind of governance and policy stuff.
Not out of the top of my head, but let me hand the answer to you maybe a bit later. Have a closer look at this, but
in the channel, you can reply to the Slack channel or tweet about it. Let's see. Okay. So I think there are no more questions. Again, thank you very much, Claudia.